On this episode of MRI Physics Explained, we're going to take a look at an incredibly popular video floating around out there on the topic of MRI. The amazing video titled The Insane Engineering of MRI Machines by the Real Engineering YouTube channel. I personally love this channel, but some of you have been asking me, how accurate is this video? How close did they get to the ever-elusive truth on all things MRI? So we're going to see where they hit the mark and where they may have fallen short on this episode of MRI Physics Explained. So I just want to make something clear before we start. I think this is an amazing video. For any of you who have tried to make sense of MRI physics, what they were able to cover in under 20 minutes in this video is astonishing and deserves a lot of praise. And they were able to put some world-class visuals to these difficult concepts. That being said, and as many of you have found out the hard way, when you try to dig a little deeper, you quickly find that certain things don't make sense if not accurately explained. So the purpose of this video is to steer you around potential conceptual stumbling blocks rather than try my hand at being a professional video critic. So with that, let's take a look at the first clip.
Imaging in medicine relies on collecting signals from the body based on the innate physical properties of tissues. Ultrasound imaging relies on how sound waves bounce off tissues of different densities. X-rays form images based on the absorption of high-energy radio frequency waves.
Okay, so claim. X-rays form images based on the absorption of high-energy radio frequency waves. Okay, let's just get this one out of the way quick, and this may be a slip of the tongue as we will be discussing radio frequency waves throughout the lecture. X-rays are not radio frequency waves. They are X-rays, right? It's in the word there. A quick look at this diagram of the electromagnetic wave spectrum shows X-rays here, above both visible and ultraviolet light. They are high energy and cause ionizing radiation, which has the potential to harm the body. Radio frequency waves are way down here, are very low energy, and do not cause ionizing radiation, but can deposit energy into tissues. Next clip.
Spin makes particles behave like tiny bar magnets. The proton inside the hydrogen nucleus behaves like a magnet. The orientation of its magnetic north is described probabilistically. Under normal circumstances, this probability is evenly distributed. This means the combined magnetic field of many hydrogen atoms cancels out. But this changes when the hydrogens are inserted into a large external magnetic field, just like the ones MRIs create.
Claim. Hydrogen protons align with an external magnetic field. This is true. We usually simplify this by showing the protons aligned either with or against the magnetic field, the orientation aligned with being the most energetically favorable. But as always in MRI physics, you can go down a rabbit hole on this, and the truth is that there is more to the story. This equation describes the probability we'll get a spin in that energetically favorable orientation aligned with B0, versus the less energetically favorable orientation aligned against B0. But you can see this equals the differences between the two energy states divided by a constant and the background temperature, i.e. the background energy from the random motion and collision of particles, which tends to equalize the energy difference. So if we cool everything down close to absolute zero, you can see that nearly all the protons would align in the most energetically favorable state in the direction of the external magnetic field because we remove that equalizing background thermal energy. But the problem is, in reality, we're not at absolute zero. We're at body temperature. So we have a background thermal energy from random molecular motion and resulting collisions that on average causes an equal distribution of the proton orientations. And in the absence of a strong external magnetic field, we get no net magnetization. But when we apply a strong external magnetic field, we're able to overcome this background energy just ever so slightly that allows us to build a net magnetization. And that's also why the stronger the magnetic field we apply, the more we can overcome this and the larger the net magnetization we can build. So going back to Real Engineering's graphic, it's actually really accurate and showing the more precise picture of what's going on. Great job on that one. Okay, next clip.
Common MRI field strengths are 1.5 to 3 Tesla. around 300,000 times stronger than the Earth's magnetic field.
Claim. Common MRI field strengths are 1.5 and 3 Tesla, around 300,000 times stronger than the Earth's magnetic field. Another partially correct. The most common MRI field strengths are indeed 1.5 and 3 Tesla in the clinical setting. But if we do the math here, and this is important to know for board exams, the Earth's magnetic field varies but equals approximately 0.5 Gauss, and 1 Tesla equals 10,000 Gauss. So if we do a little math here, a 3 Tesla MRI machine would have a field strength equal to 30,000 Gauss, which equals 60,000 times the strength of the Earth's magnetic field, not 300,000. Next clip.
Higher magnetic fields require higher electric currents that would melt ordinary wires. To achieve larger currents in the wires, engineers required superconducting coils. This means that the main superconducting coil in MRIs does not consume any power directly. Rather, the main consumption of energy is just to keep the coil cooled down, so the current will travel endlessly, leaving the MRI magnet permanently on.
Claim. The MRI magnet is always on. This is true. Pretty wild technology, right? Once they charge the main superconducting magnet and cool it down, as long as the coolant system functions appropriately and maintains the temperature, the magnet is always on, which is amazing but also the source of countless accidents where people mistakenly believe that since the machine is off, so is the magnetic field, and bring ferromagnetic objects into the room, sometimes with deadly results. You can see just how powerful the magnet is in this clip. And in emergent situations, say someone is pinned inside the MRI machine against one of these metal objects, you may have to do what we call quench the magnet, quickly dumping the coolant which allows the superconductor coil to heat up and lose its magnetic field. But be warned, this is extremely loud and can cause hearing damage, a favorite board testable fact. You'll also want earplugs for when your manager begins yelling at you for the hundreds of thousands of dollars it will cost to recool and recharge the MRI machine. Okay, next clip.
Once the atoms are aligned in the machine's incredibly strong magnetic field, the machine gives them a tiny nudge using a magnetic radio frequency pulse.
So claim, the machine gives a radio frequency magnetic pulse. True. Recall to all the way back in the first lecture when we covered this topic, and how we can use an electromagnet with an alternating current to create a magnetic pulse. When applied at the Larmor frequency, which if you do the math happens to be in the radio frequency range, this physically displaces our net magnetization away from the B0Z axis. Next clip.
This nudge misaligns these hydrogen bar magnets to shift their magnetic field perpendicularly to the large magnetic field the machine is creating. Naturally, the spins want to align their orientation back to their original position, aligning with the machine's magnetic field. But they don't fall back immediately. They decay in a spiraling motion. This decay causes a changing magnetic field, and by placing a coil of wire nearby, this changing magnetic field can induce currents that can be read as a clear signal.
Claim. The spins decay back to align with Z, or the B0 axis, in a spiraling fashion. We're going to give this a true and a false. What was said is essentially correct, but the graphic shown here is the classic conceptual trap when teaching MRI physics. This depiction of the net magnetization is wrong. It does not spiral all the way up, perfectly realigning with the Z-axis back to its full net magnetization. In reality, the net magnetization fades out quickly due to T2 decay, way before it has time to rebuild along the Z-axis as shown here. We then have to either make it re-emerge as an echo or wait for it to rebuild in the background, which we can't see, before exciting the system again with another RF pulse. This may seem like a small detail, but conceptually means all the difference in the world when trying to understand T1 and T2 contrast. Check out the dedicated lecture on T1 contrast for more information. Link above, and do not fall for this conceptual and very pervasive misleading visual. Next clip.
Recall that MRIs detect signals from the spiral decay pattern of hydrogens after they've been nudged. These spirals decay with a unique rotational frequency. Interestingly, this is the only frequency that can nudge the hydrogens too.
Claim. The detected signal is the only frequency that can nudge the hydrogens too. We're going to give both a true and false on this, and just make a slight point to avoid any future conceptual issues. This isn't such a clear-cut fact, and as we discussed in Lecture 1, all electromagnetic waves will impart energy to the system, but ones near the Larmor frequency, which is the natural frequency of the system, will most efficiently transmit that energy. This is the resonance in magnetic resonance imaging. Think of the analogy of the singer breaking the wine glass by singing intensely at its natural frequency that we introduced in Lecture 1. Continuing with this clip.
Luckily, rotational frequency is dependent on something we control, the magnetic field strength.
Claim. Rotational frequency is something we control via the magnetic field strength. This is true. Remember that the vast majority of what we do in MRI physics is governed by this amazingly simple looking formula of the Larmor frequency, which equals a constant, which we cannot control, times the magnetic field strength, which we can control. Okay, next clip.
If we apply a gradient to the magnetic field strength, we can selectively nudge atoms along the gradient by applying the corresponding frequency. To image a slice near the weaker end of the tube, the machine sends a nudging pulse centered at the lower rotational frequency, say 63.998 MHz. And to image a slice on the other end of the tube, the pulse is centered at 64.002 MHz.
Claim. Gradient magnetic fields are applied to select a slice via a tuned RF pulse. True, and very good on this one. This is not an easy answer to find. If you want further information on how we create these gradient magnetic fields, check out the dedicated lecture on slice selection, link above. And just remember, this is only for 2D imaging. For 3D imaging technique, we are imaging a cube of matter, not a slice, and therefore we replace the slice select gradient with a second phase encoding step. Next clip.
We need to contrast the tissues using two different signal types. The first one deals with how quickly atoms realign themselves with the large magnetic field after a nudging pulse. This is called T1 relaxation. The second measure comes from the physical reality of interaction between hydrogens. The atoms do not realign with the magnetic field uniformly. In tissue, hydrogens interact with each other and with their surroundings. Right after the nudging pulse is sent, the small interactions cause the spins to fall out of uniformity. Since the coil can only measure the sum of all of these spiral decays, then the falling out of order would create a decaying signal. This is called T2 decay.
Claim. T1 equals proton realignment, T2 equals local spin interactions. True. I think this is as succinct and accurate of a statement you can make for an introductory video, but just remember that T1 and T2 are not actually two different signal types. The machine only sees one signal, and that is T2 decay. T1 and T2 are physical properties of tissue that affect our signal. Okay, next clip.
We can emphasize the T1 signal by sending pulses rapidly and listening to the signal immediately, as the dephasing effects of T2 do not have enough time to take place. We can emphasize T2 by sending pulses slowly and listening for longer, allowing the dephasing to occur, the time between pulse repetition and how long to wait to listen for a signal. These two parameters are chosen by the technician each time an MRI is performed, and they choose them depending on what the doctor would like to image.
Claim. Emphasize T1 signal with rapid pulses and listening immediately, T2 signal by sending slow pulses and waiting longer to listen. True. Again, very good job of trying to summarize an incredibly difficult and in-depth topic. One that we spent 3 dedicated lectures on to flush out all the details. Check those out if you want more information on how this all works. Next clip.
The signal is collected as a sum from a singular slice. The machine needs to form a 2D image of each slice. There is one extra layer of complexity, since the receiver coil can only measure the sum of the signals from all the decaying hydrogens in the slice.
Claim. The receiver coil can only measure the sum of all signals from within the slice. True. Again, a subtle but critical point we reinforced over and over. We can only detect the sum of all the signals coming from each voxel of a slice, which is a problem if we want to build a picture based on the signal coming from each individual voxel, which brings us to the most complex but fascinating topic. How do we build a picture, which we'll discuss shortly. Next clip.
It is easier if we imagine the slice as a grid of rotating hydrogens, where we color the phase of the atoms in grayscale. When rotating in unison, the grid is all white, and atoms rotating 180 degrees out of phase are colored black.
Claim. Spins are color-coded in grayscale according to their phase. False. This one is just plain wrong. We are not encoding color according to phase. But
using another set of gradient coils, MRIs precisely change the phase of rotating hydrogens to create striped patterns. By controlling how long the Y and X gradients are turned on, the MRIs can create patterns in all directions and frequencies. Slowly, the machine starts to imprint all the patterns with different frequencies and orientations to sample their relative strengths in physical space. And slowly, by adding more and more patterns, the image starts to emerge. This is what forms the image for each 2D slice.
claim. Images are created by adding patterns of black and white lines. True. This one is interesting. We are now getting closer to the truth of how this works, and bravo for the team at Real Engineering for getting this far. They definitely went way beyond any MRI physics review course to find this answer, and likely talked to some real MRI engineers. We do indeed add patterns of black and white, something, together to build an image, but they aren't simply stripes. But why this works is still perplexing. Why would this result in an image? And how do we tie this into K-space? Those answers, my friends, I have not seen anywhere, but the explanation is more beautiful than you can imagine, and we will cover it in future lectures. Okay, next clip.
Gradient coils rapidly turning on and off are the source of the loud clunking sounds in MRIs.
Claim. Gradient coils rapidly turning on and off are the source of the loud clunking sounds during an MRI scan. True. In fact, while most people do not enjoy this sound, some have developed an unhealthy fondness for it.
Magnetic resonance imaging. Magnetic resonance imaging.
Okay, let's go back and watch a clip near the very beginning and see if we can address a major question.
Prior to their introduction to medicine, we peered inside our bodies using harmful ionizing X-rays or low-detailed ultrasounds. While incredibly useful, even to this day, these two imaging techniques pale in performance to the safe millimeter resolution of MRIs, capable of creating a 3D reconstruction of the body rather than a flat 2D image.
Claim. MRI is a superior form of medical imaging. False. But sometimes true. There are several claims here we need to address, both historical and technical. They failed to mention, I think likely intentionally because it might take away from the awe of MRI, the most popular form of cross-sectional imaging and maybe the most popular form of medical imaging in hospitals, computed tomography, or as you know it, a CAT scan. CT scans were developed about a decade before MRIs were, and today can scan patients so fast they have to strap them down to the table to keep them from flying off. We can even create 3D models and even 4D images, folks. 4D. I wonder if it's like those 4D movies where they blow air and water in your face during the scan. Anyway, CT is far cheaper and faster than MRI. The downside being it does expose you to ionizing radiation, whereas MRI does not. Now let's talk about this resolution claim. This actually is a deep topic because we are all familiar with numbers associated with resolution. How many of you have a 4K TV? But here's a more important question. How many of you have a useful 4K TV? If you didn't pay for that 4K Netflix membership, will you get that amazing detail on your 4K screen like those gorgeous pictures that hit you every time you walk into Costco? So in medical imaging, what we care about is useful resolution. How well can we delineate contrasted objects from one another? And the way we do this is by measuring the line pairs per distance, usually millimeters. As you can see here, we have a black and a white pair of pixels, together measuring 1 millimeter across, and you can see them perfectly. This would be 1 line pair per millimeter. Now let's add another line pair. Can we still make them out? You bet we can. So this would be 2 line pair per millimeter. What about 8 line pair per millimeter? Still good, right? So you can see that if we continue with this, there is going to be a point at which we can no longer differentiate the line pairs from one another. We do not have the resolution to do so. This will be the useful resolution of our medical imaging, and it's based both on our detector element size, the monitor displaying the image, and the background image noise. Here is a chart that shows typical values of this useful resolution across multiple imaging modalities, and notice where MRI is. Second to last, a cheap X-ray has a far superior resolution to both MRI and CT, which brings us to the most important question in medical imaging. What is it you're trying to see? Sure, this MRI of the brain looks pretty, but let's say a patient got into a car accident and you are worried about a head bleed. Do you need a fancy MRI scan to diagnose that? Nope. A quick and cheaper CT scan is great for seeing acute bleeds, like this one in the right frontal lobe. What about fractures? Look at this picture. It's from the same CT scan, just processed in a different way, and appreciate how you can see these very fine fracture lines associated with this deformity along the right frontal bone. The video mentioned 1 millimeter resolution of MRI. Well, these CT images are 0.5 millimeter thick. 0.5 millimeter. And unlike MRI, if we want a different slice thickness, we can just reprocess the raw data into the thickness we want. We can even create these fancy 3D models of the skull from that same CT scan within seconds. Can we see these fractures on an MRI? No. You can make out there's a deformity there, but MRI isn't great for characterizing subtle fractures. Better seen on CT. But let's say a different trauma patient comes in and everything looks normal on the CT, shown here. But the patient is acting more and more altered. We think he may have a more serious shearing neuronal injury. So we order an MRI, and lo and behold, we see all these tiny microhemorrhages that were beyond the resolution of CT, but we can bring out on MRI, suggestive of a diffuse axonal injury. What if you're worried about pneumonia? Does this multi-$1,000 MRI of the chest show more detail than a cheap old-fashioned X-ray? I think you get the point. The superiority of medical imaging really comes down to what it is you're hoping to assess for, and which imaging modality is best visualizing it, whether it be an MRI, CT, ultrasound, or a plain old X-ray. So we're going to finish this up with a few clips, starting with the B-roll of shame.
Magnetic resonance imaging, however, relies on something far less intuitive: the quantum properties of the hydrogen atom. For research purposes, MRIs can produce even higher magnetic fields, up to 20 teslas. This framework can be extended to 2D grayscale geometries. In reality, what does this mean for the spinning hydrogens? What is the physical representation of these patterns? The MRI machine is a truly astounding piece of electronic technology.
Come on now, this is a lecture on MRI. You can't be showing pretty CT pictures while discussing MRI and hoping no one will notice. And a quick bonus.
The MRI machine is a truly astounding piece of electronic technology, and developing something this complicated would simply not be possible without diagnostic tools like those created by Keysight.
Claim: MRI machines wouldn't exist without diagnostic tools like those from Keysight. We're going to give this a true, as you can only imagine what kind of sophisticated instruments were required to pioneer the MRI machine, but more importantly, let's applaud this company for supporting science and education content creators such as Real Engineering. Maybe I'll make it to the big leagues someday. So next up, we're going to step up the complexity and begin our series of lectures on pulse sequences, starting with the concept of the echo. And that's all, folks. Again, huge amount of credit to Real Engineering for tackling such a complex topic. They did a better job than most paid MRI physics courses, so big round of applause, and we'll see you next time on MRI Physics Explained. This is Dr. T.E. signing off.